Couple extra problems this time, starting with number 6. We got double problem setups here. A block of mass 2 kilograms initially at rest is pulled along a frictionless horizontal surface with the force shown as a function of time. Question 6. The speed of the block at t equals 3 seconds, and we have here a changing force. A changing force makes the kinematic equations hard to use. A changing acceleration, but we have impulse is equal to change in momentum. When you see the force time graph, you should think to yourself, impulse is equal to the area under that graph, a triangle. 1/2 base times height, that's the impulse, is equal to the change in momentum. We started at rest, we have a base, we have a height, we have a mass of 2 kilograms. The velocity is 6.75 meters per second. A lot of people said B, 4.5 meters per second. I don't know how you got that. I bet I can figure out. I couldn't figure out how you got that. So if you got B, let me know how you got B, but the answer is C. Next, we got a double question here. 7 and 8 together. The center of mass of a cylinder of mass m, radius r, and rotational inertia I is 1/2 mr squared has a velocity of the center of mass v cm. It's rolling without slipping. That's key. Without slipping along a horizontal surface and encounters a ramp of angle theta, but we don't care because we're talking about energy here. We're talking about energy when you're talking about the maximum height the cylinder reaches. This is an energy problem. Anyway, we have kinetic energy converted into gravitational potential energy. Two types of kinetic energy, the 1/2 mv squared and the 1/2 I omega squared. And 1/2 I omega squared, of course, cleans up very nicely. We have I is 1/2 mr squared and omega, v equals omega r, so omega is equal to v over r, and the r's cancel out and the m's combine, and 1/2 and 1/4 is 3/4. And what were we asking for? Yeah, height. Height is equal to 3v squared over 4g, and that is, as you can see, option D. On to number 8. It's the same sort of thing, but number 8's more wordy. Now, the cylinder is replaced with a hoop. Cylinder is now a hoop. It has the same mass, same radius. The mass cancels out, but same radius. The hoop's rotational inertia is mr squared. Well, we don't really care about radius either. Anyway, the hoop's rotational inertia, mr squared. The center of mass, the hoop, has the same velocity as the cylinder when rolling along the horizontal surface, and the hoop also rolls up the ramp without slipping. How would the maximum height change? Well, we have this sort of situation. The translational kinetic energy plus the rotational kinetic energy is converted into gravitational potential. What you're telling me with this new I equation, mr squared, no more half, you're telling me that k rotational is increasing. The rotational kinetic energy is increasing, and if you do that, then you'll increase your gravitational potential energy, and the answer is A. Most people said C, which is the opposite of what's true. If the rotational kinetic energy increases, the gravitational potential, the height will increase. We kind of did this backwards in class. We did this where we let both of them go, and we said the cylinder we let them go from the same height, and the cylinder is faster and the hoop was slower. And if you sort of turn that around in your head and say, well, let's imagine they're going the same speed, which one would get up higher? Well, that'd be the hoop. On to 11 and 12, another double question pair. This is the test of the question pairs. A lot of free body diagrams here. Number 11. Which of the following best represents a free body diagram if it's moving at constant velocity? Key phrase there, constant velocity. Alarm bells go off in your head when you hear constant velocity. The answer is C. Why is the answer C? Well, we have constant velocity, no acceleration, no net force. Add those arrows together, they cancel out. On to number 12. Which of the following best represents the free body diagram of a box? Speed increasing, moving down the incline. Speed increasing, moving down, so that's going to be E. Now, how do we know it's E? Well, we are moving down the incline because friction is up the incline. Friction always acts against the direction of sliding, and we have an increasing speed because it's net force down. Net force is down the incline. Most people said B, and I agree that B is sliding down the incline, but B is not speeding up as it goes down the incline. B, if you put those arrows together, B is slowing down. So the answer is C. Only one that is speeding up and sliding down. And number 28, the graviton, a carnival ride. It looks like a large washing machine, spin cycle type thing. People stand in the cylinder and it spins, and then the floor is removed and they don't fall because that would be a lawsuit. Given the coefficient of friction and the person's clothing, well, mu, tangential velocity, v, what on earth are they talking about? Well, they're talking about this and they're talking about that. we are circular motion, and I wanted to include this because even though gravitational motion is not on the AP test this year, circular motion is. So we have a net force towards the center. It's not in equilibrium. Net force towards the center causing you to stay in uniform circular motion. The normal force is that central pointing centripetal force. Normal force is equal to mv squared over r. Friction force and gravitational force cancel out like that, so let's rearrange a little bit. With friction is equal to normal force times mu. Rearrange a little bit more. We have normal force is mv squared over r. Normal force is mg over mu. Let's get those guys together. And what on earth was I talking about? I was talking about mass. I was talking about what mass do you need? Well, looking at the mass cancels out. What mass do you need? Mass cancels out. None of the above. That's the answer, because mass cancels out, which kind of, you don't have to go through all that derivation there. You kind of think about it. On the right, we have a sock. On the left, we have two socks kind of together a little bit. How fast does it need to be spinning in order to keep one sock or the two sock system stuck to the wall? Same speed, mass cancels out. Thank you, Galileo number 32. Physics students checking constant acceleration equations. They drop a tennis ball 6 meters. The predicted velocity 20% above the velocity measured by the photo gate. So why is that? We have air resistance. When you first drop the tennis ball, a little bit of air resistance acting opposite the direction of the velocity. As the tennis ball goes faster, air resistance increases. It is related to velocity proportional to either velocity or velocity squared. We did that experiment with the coffee filters. Anyway, A, the ball changes shape while falling. I'll change your shape while falling. B, the acceleration of gravity. No, the acceleration of gravity never varies. Get out of here with B. C, air resistance increases the acceleration of the ball. A lot of people put C. That was the most popular answer. Air resistance increases. Well, you see air resistance and you're like, yeah, it's air resistance. But it's not C. It can't be C. Look at air resistance. That's not increasing your acceleration. Air resistance is fighting against your acceleration. Eventually, air resistance is so great that you are at terminal velocity. Air resistance does not increase it decreases your acceleration. Get out of here, C. What about D? The acceleration of the ball varies with the velocity. Yeah, I think that's it. What about E? The acceleration of gravity change. No, it's not E. It must be D, because the acceleration of gravity never changes. And this leads us to the next double question. It's another air resistance question. 33. An object launched and follows the dashed path shown above if air resistance is considered. That makes it harder. That makes it harder. When is the velocity of the object greatest? When is the acceleration of the object greatest? Let's do velocity first, and it's A. That's when the velocity is greatest. You might think that the velocity at E would be pretty big too. Well, not if air resistance heats up the atmosphere and steals some of your energy, so E can get out of here. And what about the greatest acceleration? While you're being shot upwards, so the air resistance is down. In the last example, you were dropped down, so the air resistance was up. Now you are shot upwards, the air resistance is down, so the answer to the greatest acceleration is A also. The results on this week's test weren't as good as the results on last week's test. I think the reason for that is because this week's test was harder.